Welcome back to the Penny Math Teacher. So we're going over systems today, expectations. Remember to use twice this video's length to take notes, wonder, ask questions. Make sure you're using that time to write everything down and keep it organized. You can actually read it because these are notes to your future self. So make sure that you can read them, especially 5 days from now or whenever else you're going to look back at them. So we're going to set up our objective. We're going to find solutions to a system of equations or inequalities. So we'll go over what a system is and how do we use inequalities with that by graphing, substitution, or elimination. So this one objective is going to last us this whole unit. It's going to be 4 videos, one on graphing, substitution, elimination for equations, and then we'll take that knowledge and extend it to inequalities. And then I'll set us up for our comprehension questions that will also go for all 4 of our videos. So this is the back page of my table of contents. So we're going to be doing these 4. So if you want to list them out, I'm putting the page numbers on the left-hand column in that margin just so they have that extra red line. Because why not? So moving on to page 36. So we're going to solve a system by graphing. I'm going to move my mouse out of the way a little bit. Okay, so we're going to first define what is a system of equations. So we learned about parts of a system, at least I learned about them in 5th grade. And we had some games at home that went over parts of systems, but systems have multiple parts. They work together to do things. So a system of equations is multiple equations that work together. And definition of multiple parts would be 2 or more. We're going to deal with just 2 for this unit. As you work into Algebra 2 and pre-calc and college and graduate math, you're going to be seeing systems with more than just 2 constraints. So we are going to be, its definition is 2 or more. We're working with just 2 for this unit. Equations or inequalities, because we are going to deal with systems of inequalities on our last video, where we want to know what values make the system true. So our solutions are solutions to all of the equations, and those values have to be the same for all of the equations, all the parts of the system. So we've solved equations before where a solution makes an equation true. So for instance, if I have x plus 3 equals 12, the solution will be x equals 9. The solution is not x equals 8. 8 plus 3 does not equal 12. Only x equals 9 makes it 12. But now, and since our graphing unit as well, so now a solution makes both or all of the system, all of the equations true. And I do want to note that we are now working with not just one equation of one variable. We're now dealing with 2 equations with 2 variables. So we have 2 equations with 2 variables. So whatever the solution is in this case, it's going to look like a coordinate. Sometimes, not every time, but if there is one solution, it's going to look like a coordinate because we have to write out the x that makes this true and the y that makes it true. So note that if we had one variable, it's just one variable equals that number. When we have 2 variables, we list it as a coordinate because that's how we can list 2 variable values. So we're going to have 4 examples. So as we go through this, we're going to have 1, 2, 3, 4 examples. And then on the bottom, we're going to look at how many solutions are actually possible and what those would look like in each of those situations. So our first example is going to be y equals negative 1/3 x plus 3. And actually, yeah, never mind. You can do the one that I just wrote up here on your own. I did a typo. I forgot to put the 3. I put a 2 instead. So we're going to sketch our axes. And I guess right now let's just set up all of them. That way you know you have the room. -4/3 x plus 5. Y equals -4/3 x plus 5. Sketch the axes. 3 and 4. 3 is going to be y equals 3x plus 1, y equals 3x minus 1. And then y equals 4/5 x minus 1. Y equals -5/4 x plus 2. And then in whatever little space you have left. So how many solutions can you have? And we're going to do 3 graphs down here. They're just going to be sketches, so they don't have to be perfect, but we're going to do 3 little sketches down there. So that is what the rest of it's going to look like. I'm going to use a pen for the rest of this, just so it's more streamlined and pointed. Okay, so for number 1, we're going to graph these. These are both in, actually all 8 of these equations are in slope-intercept form. So when I graph these, I'm going to go up 3 for the y-intercept, go down 1, run 3. So this is my first line. So I don't move my mic. I am going to be connecting my dots down here with my straight edge. And I'll move it back up. Okay, and then the next one, I'm going to go down 4. So 1, 2, 3, 4. Go rise 2, run 1. Again, I'm going to pull it down here so that I can connect them. Now, because this is not on graph paper, it's not going to be perfect, okay? So try to keep your scale as evenly as possible on all of your axes. I mean, this distance up to the first one is kind of big, and that's probably throwing me off, because if I kept going up 2 over 1, up 2 over 1, up 2 over 1, this line, this second graph, should have actually gone through that point. So if I had been more precise with where my scale was, I mean, it still kind of goes through there. So even if you make a point that's really super large, there's more leeway. So like if I drew this second line, it still is going through all 4 of those points, but it's actually different than the first line that I drew. So just be aware that graphing on lined paper is not the most precise. Graphing on graph paper would be much more precise. And then also we're going to extend this into Desmos and graphing calculators. But we want to make sure that you know how to graph this on your own and make sure it's on graph paper if you want to be more precise. So knowing that, I want you to remember that this line, every single point on this first line makes this first equation true. If I went to 0, 3, I plug in a 0 for x and I have a 3 for y, that would be a true equation. If I have substitute -4 for y and 0 for x, that would also be a true or valid solution for my second line. So where both sets of solutions line up and intersect is the solution to the system. And sometimes systems can be written with a bracket. And so our solution to this system is going to be 3, 2, and just box that because that's your answer. All right. I know I spent 8 minutes on this already, so I'm going to graph the next 3 pretty quickly. And that way, if you want to pause, try graphing all of these on your own and then come back and see what the kinds of solutions are. So for this one, I did write the same equation twice. So I'm actually going to go 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Maybe doing your scale ahead of time will help make it more precise as well. So if I go +5, then I go down 1, 2, 3, 4, and run 1, 2, 3. I'm going to do that again, 1, 2, 3, 4, and then run 3. Okay. Connect my points down here. Okay, notice I'm going all the way through the graph. Try to go all the way through the graph. It's a good habit. And the second one is actually the exact same line. So all my solutions here is all reals or all real numbers. Both of these are ways that you can write that. You can do the fancy R, which stands for all real numbers, the set of all real numbers, because both lines intersect at every single solution. So there are infinitely many solutions, infinitely many solutions. Now those solutions then are all real numbers, but if they're asking how many solutions, there's infinitely many solutions because the solutions are all reals. So number 3, these are parallel. So when I go up 1, 2, 3, 4, 1, 2, 3, 4, see that spacing, it's going to get me. But I don't have a pencil, so. Okay, up 1, go up 1, 2, 3, run 1, and then connect those. Go down 1, go up 3, run 1, down 1, 1, 2, 3, run 1. And if I do this right, they should be parallel. So they are never going to, intersect. That's the word. Okay, so there is no solution. The fancy symbol for that is a 0 with a slash all the way through it and beyond. Okay, so there's no solution, or 0 is the number of solutions. And then on number 4, so these are perpendicular, but perpendicular lines, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Perpendicular lines do intersect how many times? 1, 2, 3, 4, and then I need 5. Wait, I did that wrong. I need to rise from here. 1, 2, 3, 4. 1, 2, 3, 4. There we go. Ignore that point. Okay. That's what I get for talking while I'm graphing. Okay, and then I'm going to go up 2, go down 1, 2, 3, 4, 5, and then run 4. Woo-hoo-hoo! So if you did this really nicely, it should look like a perpendicular angle. It should look like a 90-degree angle there. They do intersect one time. And if you gave me as an answer 0 for the y and x was like 1.8, I would give that to you because that's what your graph is telling you. Now, if we were on graph paper, this might be actually at 2, so it depends on what that is, but I'm okay with this one. It is still one solution, and that's actually how many solutions we can have. If you have 2 random lines that just go through and they intersect one time, you could have one solution. We can also have the same lines, so they overlap, so you have infinitely many solutions. And then you could also have parallel lines, which would then have no solution. Okay, so these are the 3 types of solutions, or I guess 0 solutions, that you could have. You could have 1, you could have infinitely many, or you could have 0 solutions because they don't intersect. So that is graphing. I need this one. There we go. Comprehension questions. So solve 2 times x, the quantity of x minus 3 equals 24. How do you know 15 is a solution? What does being a solution mean? What does a solution to a system look like? And now we're going to explore two different methods to solving a system. Substitutions next, and then elimination. All right. Thank you for watching, and have a great day. Bye.